So in today's class we will teach about I2C programming. Here we will do the birth rate. That means we will only send the byte slab address and then the first memory location address of the RAM inside the slab device, and that's all. And after that we will send data to that RAM memory continuously. In the before code, to send a byte to send any data, we call functions, that is byte write functions every time. But this time we will call that functions, and we will call the function only one time, and then it will by itself continuously write on those memory location. So don't think if you doesn't take the before class, then it is not necessary in this code to take the before class. So just don't think anything. So we will send this value second, minute, hour, Sunday, 14th June 2026. We will send only 26 because the last 2 bits will only be stored by this slab device GS1307 and is this memory locations. This is address of the memory locations. This actually represents the memory location. This one is RAM memory location. This is first memory locations with address 0x00. To access this memory location, we have to do it through this address 0x00. And so this data will be sent. All this data will have hex value. This one for 55 it will be hex value 0x55. For 58 the hex value is 58. For 13 the hex value is 13, and so on. Sunday is first day of the week, so it will be 0x01, and for 14 it will be hex value 0x14. June is 6 month, so it will be 0x06, and for year 2026 we will write only the last 2 bit, so it will be 0x26, and we will send in all this data in the form of binary, in the form of byte. This 5 is 101. This 5 is also 101 in hexadecimal. So we are just writing all this value in this hexadecimal. And this 5 is 101 in hexadecimal. This 8 is 1000 in hexadecimal. So we are just writing in this hexadecimal form. This 1 is 1 in hexadecimal. This 3 is this in hexadecimal. So this byte will be sent in this in I2C bus from the master device to the memory location of the slab device. That means this sending all those bytes from this CORTEX and processor to this slave device GS1307. So let's write the code. Including the library of PM4C123J6PM.H, and including the library of that microcontroller. And after this, I'm defining the slave address of that GS1307, and it's usually 0x68. Then void I2C1 implies enable void. This is I2C initializations functions. I will explain this little later. This is duplex write functions. This is for sending the data, and the address will be sent first, and then the data will be sent. So we will pass the slave address, char, memory address. We will pass the memory address, and we will also count how many bytes we send, byte count, and then char data. We will pass the data to the pointer. I will explain this function little later, because if I explain this separately, then the flow of the explaining in the flow of the code will be separate, so it's not nice, right? So we will come to the main program function first. We will just type array of 7 values, and let's just copy all those 7 values, because we are going to send those 7 values. And this our second method, our Sunday 14 and June 1 year 2026. So let's copy it. And then let's copy this value. This is our Sunday 14 and that 14 June 2026. Only this 26, because the DS1307 only store this 26, the last 2 bits, So this 0x26, let's copy. And so this is just an array of 7 values, and this is just a value all those second, minute, and this is time, and this one is day, Sunday, and this one is that, this one is month, this one is year. This is just an array and here I would like to pass the I2C initialization functions, as I didn't explain it till now, so let me explain and write the code here. So void I2C1 init void system control is using I2C GPIO equal to 0x 01. What is this register? This is 0, this is 1, and what is this? The system control is now using this RCGC GPIO, and this GPIO is saying supply a clock source to any one of the bits 0 to 7 in order to choose a particular port. I'm supplying the clock source to this bit 0, so I'm setting the bit 1 and the bit 0, so I'm choosing port A. And then the next line is system control is choosing CORTEX I2C, and this one is saying 0x 02, because in hexadecimal this RCGC I2C is saying supply a clock source to any of the bits 0 to 3 in order to choose a particular I2C versions. So that we can use that I2C module in our code. So this one is the RCGC I2C register, and we are supplying 0x02. 0x02 is 0010, then is 0010. Here it is 1, so this bit is set. That means I'm using I'm choosing I2C version 1. You can use I2C 0 or any of the I2C 1, 2 or 3, but here I'm choosing I2C 1 so that I can use it in my code. And here I'm searching GPIO-E, so I will use GPIO-E. Using the AFSAL resistor, so that, and setting it to C0. C0 means 11000000. So this GPIO-E is using AFSAL resistor, so that these 2 pins of GPIO-A is set as can be used for any alternate options or alternate functions like I2C, SPI, UART, etc. So like that. So this GPIO-A now using this port control register. So this is forget everything. This one is bit 6 and 7, and this is FF. FF means 1 and negation of FF means 0. And so we are clearing this bit 6 and 7 of port control resistor because we want to store, we are clearing the bit 6 and 7 so that we can put the value 33 of this port control resistor. We are clearing the bit 6 and 7 of this port control resistor so that we can put the value 33 in this port control resistor bit 6 and 7. Because putting the value 33 will make the GPIO-A pin 6 and 7. 6 will be used for I2C SCL and I2C SCL, and this one pin 7 will be now configured for I2C SCL. And then GPIO-A, then Siemens this and German's Joe. So we are making the bits 7 and 6 as digitals. So we can use for any digital stuff, as I'm not using that analog stuff here. Height is 1000 in hexadecimal and Joe is just. So I'm setting ODR means open drain. I'm setting this only bit 7 to 1. That means follow the open drain circuit system because this bit 7 bit is the bit where is for I2C SGA. So this bit is the bit it represents the SGA line, and this is where we are going to send all those address bit and data bit, and that means where it is connected to all those any of the device master or slave. But here we prefer all those whatever device be having the circuit with low level functions transistor, because if sometime the I2C bus is sure in some rare case or an exceptional case shared by some master, and this master may sometime may have the output circuit connected to a high level function transistor, and some may have low level function transistor, and so the high okay, level okay, output circuit may okay, sometimes the current short circuit may happen, so high level okay to low level okay circuit output circuit current may okay, pass from one device to another okay, and then short circuit may happen. So because of that okay, we doesn't want any kind of such thing, so we maintain a system where the device output okay, is connected to only low level function transistor. So because of that we are using the open drain system circuit. And then interesting, this one, the okay, whatever device we are using, we prefer okay the output to connect it to low level okay function transistor, so that there is no any kind of short circuit in the system. So circuit happens then okay in electronic system and all those stuff, okay, so circuit then plus here okay, we are using the I2C one to use the MCR resistor. MCR resistor is used for usually okay, most of the time is used for okay, setting the bit D4 to 1, and that means making a device to work as okay master. That means master function enable. So we'll just say QX okay 1 0. Okay, so what I'm saying is this okay, this is the MCR resistor, and setting the bit okay D4 to 1, then is just D4 bit to 1 master function enables to 1, making it the device to operate as a master. I2C okay, MTPR. I2C MTPR is set to okay, 7, so that okay, the data transmitted in the I2C bus is transmitted at the speed of 100 kilobit per second. So in the I2C okay, initialization functions, we first choose the port and then the I2C versions, and in this port we set it the pin 6 and 7 for alternate functions, so that we can use for any kind of functions, but we set only pin number 2 pins only pin number 6 and bit number 6 and 7. We set only 2 bits, 2 bits, 1 bit for SDA and 1 bit for SCLs. So because of that we set only 2 bit, we choose only 2 bit, and this port control bit 6 and 7 is clear, so that there is no dummy data, so that we can store the value 33 to this clear bit 6 and 7 by storing the value of 3. It means set this particular pin 6 for the I2C SL, and this pin for the I2C SDA, and this pin 6 and 7 we want to set this as digital, because everything we're going to work here is digital, as I'm not using any of the analog function also here. I'm not using analog function here, and then this one we are whatever we are concerning here, we are talking only about the pin 6 and 7 and then here the pin 7 is not to connect with the open drain system. Open drain circuit in the output section of the device, so that there is a smooth flow of the smooth process in the any of the stuff in the circuit, and not any kind of short circuit. And then this one is selecting a device as a master, so that we can use in our transmission process. And this one is speed of the data at the rate of 100 kilobit per second. And then we will write the I2C function for transmitting the address and the data. But before this, let me write another functions. This function is not related to I2C, but we are just writing here so that here the system is using the CPACO register, and setting is value to 00F 00. This value F is 1, and this will make this set. This 2 bit will set the coprocessor 11, and this bit will set the coprocessor 10, so that the ARM Cortex coprocessor will use the floating point unit of the system, because sometimes in the code we use float or double value. So because of that, only this function and nothing else. Next we will write the code for the I2C. Here we are using the URS3 brush write for sending the address and the data. So in we will pass the step address, we will pass the memory address, we will count how many bytes to count, and then we will use pointer to pass the data. And then here the stack variable called hero, and here we will say if byte count less than or equal to 0, then there is nothing byte to send. There is no data to send. Then return -1. -1 means stop executing the function immediately. And then if there is data to send, then we will pause. We will transmit the slab address first, because we will transmit the here. If there is data to send, then after the start the first address is sent, so we will send the address. So I will store the address in the MNC register. So So I2C 1 implies I2C is now using MSA register to store the slab address, which is shifted one time to the left because address is stored from the bit 1 to 7 on, because slab address is only 7 bit, and so here here the address is slab address is only 7 bit, and then they store from 0 to 7 only, and 0 bit is not used for storing the slab address because it is only for whether we are receiving from the slab device or whether we are sending then transmitting to the slab device. So as the slab address is stored from 1 to 7 only, 1 to 7 only, so the slab address here we consider is 68, so 6 is this and 8 is 1000, this one. This is 6 and this one is 8, and since it is stored from bit 1 to 7, bit this one 0 is bit 0 is not used for storing address, so and for the address is stored from bit 1 to 7 only. So we are shifting to the left 1 times, and then we are storing the address from bit 1 to 7. So we are shifting to the left. This means shifting to the left. This means 1 times. And then address is stored from bit 1 to 7. And then here we will also store the values of memory. First, memory location of the RAM inside the slab device, that is 1307. So we will store the memory address in the MTR register. MTR register is the 32-bit register, whereas bit 0 to 7 is used for storing the data that we will transmit during the I2C transmissions in the bus from the master to the slab, and vice versa also. So this is the I2C MTR register, and in this data will be stored from the bit 0 to 7. All this the data that we are going to transmit in the I2C bus from the master to the slab. So I2C bus, we will store the memory address and this memory address, the first address shows be 0x00, because this address is this, right? The first address in the RAM memory of the slab device GS1307, the real-time clock device. And since address is 0, the slab address and memory address is 0, we will start transmitting those address. So I2C implies MCS equal to 3. 3 means this 3 means 0, 0, 1, 1, and 1. Okay, here is run, and this one is the start bit. As we are sending the slab address and memory address, that means we are we are transmitting the slab address and memory address. The slab address is sent to choose a particular slab device, and so as we are transmitting the address, that means sending or writing, so we will use this MCS register as write control register. As we are transmitting, sending or writing the slab address, we will use this MCS register as write only control register as we are writing those slab address, or sending or transmitting the slab address. So here we want to use the bit run and then start. Run means execute whatever command need to be run, and start means for all those process necessary, and then we will set this bit so that transmission is started. So as the start bit is set, the transmission will be now started. As the transmission is started, the I2C bus will be busy. The I2C bus will be busy. So here the bus is going to be busy. So let me write these functions here. As the transmission is already started here, because this bit is the start bit, and so start bit is set, that means transmission will start. Transmission start means transmission is going on, that means the bus is busy. The bus is busy means transmission is going on in transmitting the data. So as transmission is going on, the bus will be busy. So we will say while the bus is busy, while the bus is busy, that means while I2C 1 is using this MCS register, and this MCS register is equivalent to 1, that is busy bit, that means busy. So while the bus is busy means I2C is using MCS register, and this MCS register below is equivalent to 1, that means 1 is busy. So this line is representing busy. So when I2C is busy, this is, it is only the bus is busy means the status of the bus is busy. That means we are checking the status of the bus is busy is when we check the status of the bus. Checking the status of the bus means reading the status of the bus. So we are doing the reading functions. We are doing reading here. So this MCS will be used as read only control register because we are doing the reading function here. So MCS will be used as read-only control register, and so because of that, this busy bit is here, that is 0 bit. So this is the first bit. So we are reading that the bus is busy. So that's why this MCS is used as read control register, and its bit 1 is using its first bit is using to state that this is busy bit. So to state that I2 is busy, I2C 1 is busy. That means transmission of address is going on, because we are transmitting here the address. And transmitting the address, while transmitting the address, the acknowledgement bit is checked, and this is checking the address acknowledgement bit as we are sending address. So we will check. Well, the bus is busy in transmitting those address. We will check if there is any error, or we will check if the address is acknowledged. Like that. If the address is acknowledged, means 0x so while the bus is busy in transmitting this address, we're checking if we're sending address here, so we want to check if those address is acknowledged or not. So checking those address is acknowledged or not, will be checking this address, checking this 3 bits, that means data acknowledgement bit, address acknowledgement bit, and error. Because error is usually caused by either this address acknowledgement bit or data acknowledgement bit. So if either is not acknowledged, then error will be caused. So this 3 bit will be always in combined while checking the error. Because error is usually caused by either of this. And so we are checking here address is acknowledged or not. We want to check as we are sending address. So we will check these 3 bits. Because as I told, error is usually caused by either address acknowledgement bit or address acknowledgement bit or data acknowledgement bit. So because of that, and then here while the bus is busy, we are checking this address is acknowledged or not. But here the first that data acknowledgement bit is not checked, because we are only sending address, so only address acknowledgement bit will be checked. So this data acknowledgement bit will not be checked, and after this address acknowledgement bit, if acknowledged, then it will be 0. And after this address is acknowledged, then error will be 0, and busy bit is not considered here, so it will be 0. this one I'm talking about, okay, this 4 bit, okay, this 4 bit, this one, okay. So and here we are sending the address, so data acknowledgement bit will not be checked, only address acknowledgement bit will be checked. If acknowledged, then its value will be 0. So then address is acknowledged and error will be 0. We are not considering busy bit here, so busy bit will be 0 while checking error. So because of that, I'm writing here and data acknowledgement bit will not be checked as we are sending only address. So address acknowledgement bit will be checked, and if acknowledged, then 0. The address is acknowledged and error will be 0. Then this busy bit, we are not considering here, so will be 0. And if address is not acknowledged, then this data bit we are not considering, as we are sending only data, sending only address. And address acknowledgement bit will be 1 if address is not acknowledged. If address is not acknowledged, then error will be 1. And this busy bit, the next bit will be 0, as we are not considering the busy bit here. We are just checking the error, if address is acknowledged or not. So because of that, and so because of that, and so the bus is busy in transmitting the address, this address, this memory address, and we're checking if the address sent is acknowledged or not. If address is acknowledged, this bit is sent, no error bit. If address is not acknowledged, then this error bit is sent. So like that, the bus will be busy here in transmitting all this address, and just checking again if address is acknowledged or not in this. If there is any error, that means address is not acknowledged, then the error bit will be stored here. This error bit, that means this error bit. And so it will be like this, and after this we will check, we will write if error, then return error, and then there is error, so transmission is stopped. And if there is no error, however, then there are byte of data to send, and this is brush write. Brush write means there is one more than one data is there to send, because we are sending many byte of data here. So we will say if byte count greater than 1, that means if in burst write many data are sent, so many data are sent can be write as if there are more than one data. More than one data means byte count, the number of byte counted is more than 1, that is more than one data, that means number of byte count of data, that means there are many data to send. So as in burst write there is many data to send, so if there is if byte count greater than 1, Okay, we will not write if. Let's say we will write while. Okay, so while byte count greater than 1, while byte count greater than 1, empty, we will store the data here in the MTR register. MTR is a register where we used to store the data to be transmitted in the I2C bus. So we will store the data here. So whatever data that is passed from the, that will be passed from the main function to this data will be passed here, and then the pointer this is pointer, so this pointer will point to that data pass actually the pointer point to the address. So here in the I will explain this later. This is going to pass the address of the data, and then it will be the pointer will point to that data location, and then it will pass the data here. And then here MTR data is store, then we will just transmit the data MCS equal to 1. MCS equal to 1 means just that 1 is here we are using as run. So as we are sending the data, sending means writing the data, we are using MCS as write only control register, and we are using the run bit here. Run bit means continue the process. So we are just going to we are continue the process. This one that means run. So we will just start transmitting the data. So error equal to I2C 1 wait till done. That means here I2C 1 wait till done means I2C 1 wait till done means the bus is busy. MCS equal to I2C is now using MCS register and is equivalent to 1. That means the bus is busy. 1 means the busy bit, this one, the busy bit, because here as the the transmission of data is start. Transmission of data is start. It says to continue, okay, the process. So the transmission of data is start, and because in the I2C data transmission, okay, process, after the acknowledgement, okay, then data is, okay, sent, and data is sent, then okay, so after the acknowledgement of address, data is, okay, sent. So we are writing continue, okay. So because of that, we are writing only, okay, one here. That means continue, okay, the process by, okay, executing whatever, okay, that means executing the run, okay, bit. That means execute by continue the process, okay, by executing whatever it is necessary, continue the process, okay. So like this we are, okay, start to, okay, transmit the data. So starting of transmitting the data is started, so the bus will be busy. So the bus is busy means I2C is now using MCS register, and MCS register is, now, okay, as the bus is busy means the status of the bus is busy. The status of the bus is busy means after, okay, checking, we know the status of the bus is busy. Checking means reading. So, okay, we are now, okay, using MCS as read. MCS doing read function, and read function can be done using MCS read control register only. So we are using this MCS as read only control register, and we are using the bit 0 here. So we are writing MCS is busy, equivalent to busy bit. That means the bus is busy. That means data transmission is busy. And while, okay, the bus is busy, we want to check if the data so far sent is acknowledged or not, because the data is so far sent, we check if it is acknowledged or not. But here, okay, it is checking only the data is acknowledged, not the address is acknowledged. So data acknowledgement bit will be checked and not address acknowledgement bit. So because of that, okay, we will check if data is acknowledged or not. So this, okay, E is okay, this one, right? I have told E is, okay, we are checking address is acknowledged or not. If not, then error. So we are checking, okay, this 3-bit, okay, if here is error or not. So, okay, error is usually caused by address acknowledgement bit or data acknowledgement bit. So, okay, we usually check for error this 3-bit in combine. So, okay, if we want to check if there is no error or not. If no error, then the data so far sent is acknowledged. So we will check, okay, the data acknowledgement bit is acknowledged or not. So if data acknowledgement bit is acknowledged, then 0, then we are not checking address acknowledgement bit, so it will be 0. If data is acknowledged, then error will be 0. Then the busy bit we are not considering here, so it will be 0. And if this 4 bit is this is the 4 bit, E is the 4 bit, but here we are not considering the busy bit because we are just checking the error. So this is E111, this address acknowledgement bit, data acknowledgement bit, address acknowledgement bit, error. So if data is not acknowledged, then its bit value will be 1, and then here we are not checking the address acknowledgement bit, so its values will be 0. And if data is not acknowledged, then error will be 1, and here we are not checking the busy bit, so its value will be 0. So if data is not acknowledged, then this value will be returned, that means error is 0. If data is acknowledged, then this value will be returned. So here the bus is busy, so that means data is transmitting and checking if there is any error or not. If there is error, it will be stored here. If error, then return error, and then transmission is over. Then the byte count will be let's reduce by 1, and so like this the while loop will process. So by this the while loop will be processed. First this is the data to be sent through the I2C bus, and then this is the when bit continue the process by executing whatever necessary, and then here the bus is busy in transmitting all those data and checking whether the data is the data so far sent is acknowledged or not by checking the data acknowledgement bit. If it is not the data acknowledgement bit is not set, then error is 0, so error will be stored here. And if any error, then is the execution will be stopped, and if there is no errors, then the byte count will be reduced by 1. So it will continue this process until the byte count is equivalent to 1. That means when there is only 1 byte left, then this while loop will stop. Until the byte count is greater than 1, this process will start. This process will continue. So data will descend one by one, next by next, and then next by next, the data will descend, and it will continue until it is greater than 1. So and it will stop only when 1 byte is left. So let's send the last byte, because this process will continue sending of the byte one after another will continue until only one byte is left. So let's send the one byte that is left. That means the last byte, and we will store in I2C 1 MTR register the last byte left, and then let's start the transmission process. Fine means 1 2 1. Fine means this one is run and this one is stop bit. So it says execute whatever whatever need to be executed that is necessary to continue the process. And this means after sending this byte, after sending this data, that means the last byte stop the transmissions. So we will send the last byte So here this function says the bus is busy in transmitting the data. That means MCS is now equivalent to 1. 1 is busy bit as the bus is busy. So the status of the bus is busy. That means we know the status of the bus is busy by checking. That means we are reading. So MCS is now used as read-only control register. MCS is now using as read-only control register, and we are using the bit 0 to say that the bus is now busy. And while the bus is busy, we are checking if the data so far sent is acknowledged or not. So MCS now equivalent to 0x 0xe. So E is we are here sending only the data. So this data acknowledgement, this is for data acknowledgement bit is set or not. If data acknowledgement bit is acknowledged, then value will be 0. And here we are not checking the address acknowledgement bit, so its value will be 0. If data is acknowledged, then error will be 0. Here we are not considering the busy bit, so its value will be 0. And if data is not acknowledged, then its value data acknowledgement bit will be 1. Here we are not considering the address acknowledgement bit because we are not sending address, and since data is not acknowledged, then error will be 1. And then here we are not considering the busy bit because we are checking only the error, and error is caused, this error bit is caused this error bit is caused by either address acknowledgement, this address acknowledgement bit, or data acknowledgement bit. That's why we are checking only this string. If data is not acknowledged, then this bit will return. If data is acknowledged, then this bit will return. So here the last bit is sending and checking if the bit so far sent is acknowledged or not. If not acknowledged, then we will store here. That error bit is stored here, and here we will check. Well, I2C1 implies MCS 0x 40. That means here the bus is busy in transmitting, but here we're checking when the bus is the transmission of the bus is over. That means the busy of the bus will be over. That means transmission will be complete here. This 4 is 0 1 0 0, and this 0 is this. That means this means the 6th bit. The 6th bit is the busy bit, and when this busy bit is low, the transmission is complete. So when this busy bit is low, the transmission is complete. So that's why we are writing here this busy bit is this busy bit MCS is now referring to MCS is now value 0x40. That means we are referring to the busy bit, and this busy bit will be when it is low, transmission will be complete. So in this line the transmission will be complete after the bus is busy for a while. But remember, see something, when the transmission is complete, the program should check the error bit and set it to address acknowledge or data acknowledgement bit set. Here it says set. So because address is either caused by error is either caused by address acknowledgement bit or data acknowledgement bit. So we will just, in the next line of code, we will just set that error to that address acknowledgement bit or data acknowledgement bit. So I2C is using the MCS register and 0x E. So I2C is now using MCS register and is equivalent to 0x E. That means it is now checking and setting. E is, this one is data acknowledgement bit, and then address acknowledgement bit, and then error, and then busy bit. We are not considering busy bit here, so because we are checking only the error, and this error bit is caused either by this busy address bit or this data acknowledgement bit. This one is address acknowledgement bit again. So we are setting if there is any error, we are setting that error we get from here. If there is any error, setting this error to this either data acknowledgement bit or address acknowledgement bit to check if there is any error. And then if there is any error in sending data, then this data error bit error in sending data will be returned. This is the functions. That function is this, and so it will be written here, and then that error will be set to that address acknowledgement bit or data acknowledgement bit. But here we are sending address acknowledgement bit, so it will be set to and actually it will be set to data acknowledgement bit, right? And then that error, if there is error, and then after this, if error, then return error. Okay, and then the transmission process is over as the address is not acknowledged. Okay, the receiving device doesn't want to receive anymore. Okay, the data sent by the master. So the stop condition will be, set by the master. If the data is acknowledged, then return there is no error, and so address and data will be transmitted through this functions. Here the data is transmitted, and then here address is first transmitted, then data will be transmitted in this function. And so this is just an array with 7 values, and here we will call the I2C initialization function, so that all about I2C is initialized, so that setup of the I2C initialization function is done here, so that we can start sending the data in the I2C bus by calling the I2C1 plus write function. So I will pass the value / address and then memory, because here we need to pass this slab address. I have defined it here. So slab address I pass it here, and then this is memory, and this is memory address. That means the first memory location address that are inside the slab device, and the RAM, this one. And then after this we need to pass the byte count. So byte count will be 7, as there are 7 value to pass, and then this is 7 value, this is 7 to tell all those, and then the data will be passed. So time that to time that to set. Here I'm passing I'm passing the slab address, because there is only one slab address. And here I'm passing the first memory locations of the RAM inside the slab device. As the birthright says, we need to pass the slab address and first memory location inside the slab device. That means DS1307, and this one is byte count, how many data we are going to count. And here I'm passing the address of this first value, and so like that the data will be transmit. And in the birthright, here the data will be passed through this, and then will be transmit to where, yeah, will be okay pass okay here. This is the pointer. The pointer okay will point to that address of the data, and the value of the data will be initialized and store okay in this will be set and then store okay in this mgr okay register. So okay, in this way all this data will be transmitted from the master to the slave device, memory okay locations, and like that it will be this data. Where is that? Yeah, this okay data okay here okay that address this is a pointer, and so it will point okay to the first okay data, and then so the data will be stored here, and then after that it will increment okay the location of the data, and then this data okay will be sent, and then byte count will be decrease 1. That means from okay 7 to it will decrease to decrease by 1. That means okay it will become 6. And then this okay as the this okay is already incremented before, so the next okay data will be that okay the location in index okay 1, and then that data will be stored here, and this after okay storing the data, that data pointer will increment to the next location okay, and then that data stored here will be okay pass, and then byte count will be again reduced, and so okay its value will be 5. And then okay as the data pointer already incremented, so that data okay location now will be that with index okay 2, and so okay that will be stored here, and then data will be set and byte count will be reduced, and it will be now 4. And then okay as data is already incremented the pointer location before that, then that location will be okay the next will be okay as it's already incremented before, then so the next location after incrementing there will be next location, then location okay data will be okay stored okay here, and then the data will be sent, and then byte count will be reduced. It will do until okay the last okay byte count, until this okay become okay 2. Okay, in that case the byte count here will be 2, and so it is greater than 1. So after this okay it will come out of the loop, and then we'll execute this line. So like that. So in this way okay data will be transmitted from the master to the slave. So all this data will be transmitted from the master okay to the slave device, memory locations okay it will be transmitted byte by byte, from CORTEX to this slave device. So thank you all. Let me okay I think I missed one line of code. in the main function here, okay, then we write the empty for loop. This for loop is necessary because I'm calling, okay, this functions, these two functions, and after that I'm writing, okay, this. I cannot, okay, just stop after writing, okay, this. The microcontroller, okay, cannot stop after executing, okay, this two line of code, because behind there is so much, okay, process going on, like, okay, passing all this, okay, it has to wait for some time because behind, okay, there is so much going on, all this value, okay, need to be passed, and then this address, okay, has to be, okay, incremented, and then all this count has to be, okay, reduced, and, okay, all this data has to be, okay, passed in those, okay, respective function, so it will take some time, right, in transmitting all those data, passing all those, okay, values, and then transmitting all those data to those respective memory location. So because of that, we write this for loop, okay, empty for loop, so that microcontroller go on, okay, continue, okay, executing this empty for loop, so that it will, okay, wait until all this process, okay, behind process is finished. So because of that, okay, this empty, okay, for loop is written here, otherwise the system may dead also. So because of that, so this is the way here how data is sent from the master to the select device. Thank you all for this session.